This is an AQA past paper solution. We are going to solve the exact questions that appeared in the exam paper.
Yeah, specifically, we're diving into the document titled June 2022 Exam Walkthrough for GCSE Physics Higher Tier Paper 1. And just to lay out the format for this deep dive, we're looking at a set of slides. On the left side, we've got the official exam questions.
And on the right, we have the all-important mark scheme answers.
Right, the exact things the examiners are looking for. We're going to work our way sequentially through questions 01 to 11.
So let's just get straight into it. Question 001. This one is all about energy resources, and it starts with a photo of a wind farm. The data they give us says the mean power output of this wind farm is 696 megawatts, which they note is enough to power 580,000 homes.
And right out of the gate, question 01.1 hits you with a calculation. It wants you to calculate the mean power needed for just one home.
Seems simple enough, but
there's a catch right at the end of the sentence. It says, give your answer in watts.
Ah, yeah, the classic unit trap, because the data given is in megawatts.
Exactly. If you just divide the numbers as they are, you lose the marks. First, you have to convert 696 megawatts into watts.
So mega means million.
Right. So that's 696 million watts, 696 with 6 zeros after it.
That is a lot of zeros to punch into a calculator.
It is, yeah. But once you have that total power in watts, you just divide it by the number of homes, which is 580,000.
And what does that give us?
It gives you a nice clean 1,200 watts. That's the mean power per home.
Okay, moving down to 01.2. They give us a scenario where on one specific day, the UK electricity demand was 34,000 megawatts. But wind power couldn't meet this demand, and we need to suggest two reasons why.
The mark scheme is really looking for the practical realities of wind energy here. The first big one is just reliability. Wind is unreliable.
Can you just write it wasn't windy enough?
You need to be a bit more thorough. The mark scheme accepts that turbines don't turn if the wind is too weak, but, and this catches people out alas, they also don't turn if the wind is too strong.
Wait, too strong?
Yeah, for safety reasons. They literally shut themselves down so they don't break. So wind speed is the first valid reason.
What's second?
The second is purely about scale. There's simply not enough wind turbines in the UK to generate that massive 34,000 megawatt demand.
Makes sense. So 01.3 switches to the mechanics of the turbine. It says an engineer oils the mechanical parts. Explain how oiling affects the efficiency.
This is a 3-mark question, so we need a step-by-step logical chain. Step 1 is stating the actual effect, which is that efficiency increases.
Okay, efficiency goes up, but why?
Step 2 is the definition of that increase. Efficiency increases because the proportion of energy usefully transferred, or you could write that the wasted energy decreased. Both are fine.
And the physical reason for that happening?
That's the 3rd mark. It's because less work is done against friction. The oil reduces friction, so less energy is lost to the surroundings.
Right. And to wrap up this section, 01.4 asks why people should be encouraged to use energy-efficient devices.
The slides give us 2 main points from the mark scheme here. First, efficient devices waste less energy, which means they need a lower energy input to do the exact same job.
And how does that scale up?
Well, if everyone uses less input, the overall electricity demand decreases.
Yes.
And minimizing that demand reduces the environmental impacts, specifically because we have to burn fewer fossil fuels to generate the power.
That's a good comprehensive. Let's move on to question 02. We're looking at density and practical skills. There's a picture of a hand holding this irregular, rough-looking rock.
And Arrow 2.1 asks for a full method to determine the density of that rock. It's a 6-mark question, so they want the complete level 3 response breakdown.
Since it's irregular, you can't just take a ruler to it to find the volume.
No, absolutely not. The very first step is getting the mass. You must explicitly state to measure the mass using a balance.
Okay, mass is sorted. How do they want you to get the volume?
You have to describe the displacement method. You use a displacement can, which is also known as the Eureka can. You fill it with water exactly level with the spout.
Got it. Then drop the rock in.
Carefully, yes. You place the rock into the water and collect the water that gets displaced out of the spout. Then, and this is crucial, you measure the volume of that displaced water using a measuring cylinder.
So the volume of the water is the volume of the rock.
Right. And the final mark is just giving the equation you use to finish the job. Density equals mass divided by volume.
So 02.2 gives us some actual numbers from the students. The density came out to 2.55, but with an uncertainty of plus or minus 0.10 grams per cubic centimeter. We need the maximum and minimum values.
This is just testing if you know how to apply uncertainty. For the maximum, you add the 0.10 to 2.55, giving you 2.65.
And for the minimum, subtract it.
It's exactly. 2.55 minus 0.10 is 2.45. So the range is 2.45 to 2.65.
Which fits perfectly into 0, 2.3. We have a table of rock densities. Basalt is 2.90, chalk is 2.35, flint is 2.60, sandstone is 2.20, and slate is 2.90. We have to identify the rock.
Right, so we look at a range of 2.45 to 2.65 and see what fits.
Flint is 2.60. That sits right inside the range.
It does, but look at the right side of the slide, the mark scheme. The accepted answer is chalk or flint.
Wait, chalk is 2.35. That's outside our minimum of 2.45. Why is it accepted?
It's interesting. The slide doesn't give a deep philosophical reason, but it shows the examiners allowing for experimental error. In the context of a student practical, chalk is deemed close enough to be a valid conclusion, even if flint is the mathematically perfect fit.
So you get the mark for either one. Good to know. Finally, for this question, 0, 2.4. The student only took one set of measurements. Why does taking more than one set improve accuracy?
This is a classic practical skills answer. You take multiple measurements so you can calculate a mean.
And the benefit of the mean is?
It reduces the effect of random errors. That's the exact phrasing they want. Reduces the effect of random errors.
Let's jump to question 03. Electrical power and efficiency. We've got a photo of some pavement tiles that generate electricity when people walk on them.
Question 03.1 is pure recall. What is the equation that links current, potential difference, and power?
That's P, V, and I.
Right. P equals V times I. Power equals potential difference times current.
And 03.2 makes us use it. A person steps on the tile. The potential difference is 40 volts, and the power output is 4.4 watts. Calculate the current.
So we rearrange our equation. Current I equals power divided by potential difference.
So 4.4 divided by 40.
Exactly. Which gives a current of 0.11 amps.
Moving to 03.3, it asks for another equation. This time linking efficiency, total power input, and useful power output.
The standard equation is efficiency equals useful power output divided by total power input.
And 03.4 puts that into practice. The tiles are powering LED lights. The total power input is 4.0 watts, and the efficiency is 0.85. We need to calculate the useful power output.
We rearrange that efficiency equation. Useful output equals efficiency times total input. So 0.85 times 4.0.
And this result?
3.4 watts.
Brilliant. Question 04 is thermal insulation and specific heat capacity. There's a diagram of a metal can wrapped in some insulation material with a thermometer poking out of a lid.
First up, 04.1. Identifying the variables in the experiment. The independent variable first.
The independent is the one you choose to change.
Yes. And here, that's the type of insulation or the material used.
And the dependent variable, the one you measure.
That's the time. More specifically, measuring the time it takes for a temperature change to occur.
04.2 shows a close-up of a digital thermometer, thermometer B, reading 87.4 degrees Celsius. What's its resolution?
Resolution is just the smallest change you can measure. Since it gives one decimal place, the resolution is 0.1 degrees Celsius.
View 4.3 compares this to thermometer A, which is your traditional liquid in glass stick thermometer. Why is thermometer A more likely to be misread?
It's all about how you look at it. The mark scheme says the viewing angle affects the measurement.
Like you look from above or below the line?
Exactly. The technical term they provide for that is parallax error.
Now for the heavy math in 04.4. The temperature of water decreases from 85.0 to 65.0 degrees Celsius. The energy transferred is 10.5 kilojoules. The specific heat capacity is 4,200 joules per kilogram degrees Celsius. We have to calculate the mass.
First thing you have to spot is the kilojoules. 10.5 kilojoules needs to be converted to 10,500 joules.
And the temperature change.
85 minus 65 is a change of 20 degrees.
So what's the formula we're working with?
Energy equals mass times specific heat capacity times temperature change, or E equals M times C times delta theta. We need mass, so we rearrange to M equals E divided by, in brackets, C times delta theta.
Let's plug those numbers in.
Mass equals 10,500 divided by the result of 4,200 times 20.
Which is this?
125 kilograms.
Perfect. 04.5 shows the results for two different insulations. Material X took 450 seconds to cool down. Material Y took 745 seconds. Compare their thermal conductivity.
Well, material X had the exact same temperature decrease, but it did it in a much shorter time, 450 seconds, versus 745.
Meaning the heat escaped faster?
Right. And because the rate of energy transfer is higher, that means material X has a higher thermal conductivity.
Question 05 is static electricity. A student rubs a plastic rod with a cloth. The rod becomes negatively charged. 05.1 asks us to explain why the cloth becomes positively charged.
You have to talk about electrons here. The mark scheme wants you to explicitly say that electrons are transferred from the cloth to the rod.
And because electrons have a negative charge.
The cloth has lost negative charges, so it now has more positive charges than negative charges left behind.
O5.2 takes that negatively charged rod and puts it on a balance. Then, another charged rod is held above it. The reading on the balance increases. Why?
The rod being held above is also negatively charged, like charges repel.
So it's pushing the rod down onto the scale.
Exactly. That repulsion creates an additional downwards force on the balance, which the balance reads as an increase in mass.
O5.3 says the balance actually had a zero error. Why didn't that matter for this experiment?
Because they only cared about the change in the reading. Even if it started at the wrong number, the amount it increased due to the force of repulsion is still accurate.
O5.4 talks about a spark. A spark jumps between the charged rod and an earthed conductor. Why?
It's driven by potential difference. There is a very large potential difference between the highly charged rod and the earth conductor.
And that difference causes the spark.
Yes, that massive difference forces the charge of the electrons to move right through the air from the rod to the conductor. That movement is the spark.
Okay, let's look at question 06, the national grid. We've got the standard diagram, power station, then transformer X, then cables, then transformer Y, then the consumers.
So 6.1 is about transformer X right after the power station.
Yeah.
They want to know why it's used.
It's a step-up transformer.
Right, which means it increases the potential difference. And by doing that, it decreases the current flowing through the cable.
Why is decreasing the current so important?
Because high current causes the cable to heat up. A lower current reduces the thermal energy transfer to the surroundings. Less heat lost means a more efficient grid.
06.2 asks about transformer Y, right before the homes.
That's the step-down transformer. It decreases the potential difference back down to a safe value for consumers to use.
06.3 brings a massive calculation. The energy transferred to the homes is 3.24 times 10 to the power of 11 joules. The potential difference is 230 volts. Calculate the charge flow.
The equation you need is charge equals energy divided by potential difference. Q equals E over V.
Okay, so we take that massive energy number.
3.24 times 10 to the 11 and divide it by 230.
The question specifies giving the answer to 3 significant figures.
Right, so you do the division round to 3 sig figs, and the mark scheme answer is 1.41 times 10 to the power of a 9 coulomb.
Moving on to question 07, nuclear radiation. 07.1. What does an alpha particle consist of?
It consists of 2 protons and 2 neutrons. The mark scheme also accepts just saying it's a helium nucleus.
07.2 gives us a nuclear decay equation. We have krypton, symbol Kr, decaying into rubidium, symbol R.
And we can see from the equation it's emitting a beta particle. A beta particle has a mass number of 0 on top and an atomic number of -1 on the bottom.
So to fill in the boxes for rubidium,
You just balance the numbers. The top number for krypton is 85. The beta is 0. So the mass number for rubidium has to be 85.
and the bottom number.
Krypton is 36. The beta is -1. To make it balanced, rubidium must be 37. Because 37 plus -1 equals 36.
Got it. 07.3 asks us to explain why the risk from internal contamination is different from the risk from external irradiation, or alpha radiation. 5 marks.
Chunky one. First, address the external risk. Alpha radiation has very low penetrating ability. It is completely stopped by skin. So externally, it poses a low risk.
But if it gets inside you?
That's the internal contamination part. Inside, alpha is absorbed directly by living tissue and organs. And the key phrase here is that alpha is highly ionizing.
Meaning it strips electrons off atoms.
Yes, which causes immense damage to cells and DNA. Therefore, internal contamination carries a far greater risk of harm.
Question 08 takes us to specific latent heat. We have a diagram of a heater submerged in a beaker of water on a balance. 08.1 asks what instrument is used to measure the volume of the water.
The diagram shows a beaker, but the mark scheme is very clear. You should use a measuring cylinder for accurate volume.
08.2 asks to identify a hazard in the experiment.
You're heating water, so the hazard is boiling water. It can cause burns.
Simple enough. 08.3 is the calculation. The initial mass of the water was 0.080 kilograms. The final mass is 0.071 kilograms. The energy supplied by the heater is 25,200 joules. Calculate the specific latent heat of vaporization.
First, find out how much mass actually turned into gas. Subtract the final mass from the initial. 0.080 minus 0.071 gives a change in mass of 0.0009.
And the formula for specific latent heat, L.
L equals energy divided by mass.
So 25,200 divided by 0.009.
Exactly. Which gives you 2,800,000.
Yeah.
Or in standard form, 2.8 times 10 to the 6. And the unit they want is joules per kilogram.
Now for the air analysis part. 08.4 says some thermal energy was transferred to the surrounding. How does this affect the calculated value of L?
Well, if energy escaped to the air, then less energy was actually transferred to the water than we assumed in our calculation. Because we divided by a larger energy value than was truly used for boiling, our calculated value of L is too high.
8.5 is the opposite. Some water evaporated before it even reached the boiling point.
Right, so the change in mass we recorded is too high because some of it evaporated without needing the latent heat of vaporization. Since mass is on the bottom of our equation, we're dividing by a number that's too big. The calculated value of L ends up being too low.
Question 09. Power and work done. We have a girl with a mass of 60.0 kilograms running up a flight of stairs. The vertical height is 1.75 meters, and it takes her 1.40 seconds. 09.1, calculate her power output.
2 steps here. First, calculate the work done against gravity. The formula is mass times gravitational field strength times height. M times G times H.
Gravity is 9.
Right, so 60 times 9.8 times 1.75. That gives a work done of 1,029 joules.
Now we need power.
Power is work divided by time. So we take that 129 joules and divide by her time, 1.40 seconds.
Which gives
735 watts.
Error 9.2 asks why her total actual power output is greater than this calculated value.
Because our calculation only accounted for lifting her body vertically, but she's also moving, so she increases her kinetic energy.
She's not a perfectly efficient machine either.
Exactly. Energy is wasted in her muscles, and a lot is transferred as thermal energy. Her total power has to supply all of that wasted energy too.
Error 9.3 introduces a boy running up the exact same stairs. He takes more than 1.40 seconds, but his power output is the exact same as the girl's. What does this tell us about his mass?
Look at the equation again. Power equals work divided by time. His time is larger, but his power is the same. The only mathematical way that works is if his work done is also larger.
And since the stairs are the same height?
The only variable left to increase the work done is mass. So the boy's mass must be greater than the girl's mass.
Spot on. Question 10 is elastic potential and kinetic energy. We've got a toy airplane launch system using a spring. 10.1 gives us the stats. Spring extension is 0.12 meters. Spring constant is 50 newtons per meter, and the plane's mass is 0.0200 kilograms. Calculate the maximum speed of the airplane.
This is a conservation of energy question. All the elastic potential energy in the spring converts into the plane's kinetic energy.
So calculate the spring energy first.
Yes. Elastic potential energy is 0.5 times the spring constant times the extension squared. So 0.5 times 50 times 0.12 squared.
That comes out to 0.36 joules.
Right. Now we set that equal to the kinetic energy equation, which is 0.5 times mass times velocity squared. So 0.36 equals 0.5 times 0.020 times v squared.
Let's isolate v squared. 0.5 times 0.0 is 0.01. So 0.36 divided by 0.01 is 36.
And the square root of 36 is 6.0. So the maximum speed is 6.0 meters per second.
10.2 asks us to complete a sentence about energy transfers as the plane moves upwards through the air.
As it goes up, gravity slows it down, so there's a decrease in kinetic energy. At the same time, it's getting higher, so there's an increase in the gravitational potential energy of the airplane.
And 10.3, give one way to increase the horizontal distance the airplane travels.
The MART scheme offers 2 choices. You can either increase the extension of the spring, which just gives it more starting energy, or you can increase the angle of release to give it a better trajectory.
Finally, we reach question 11, electrical circuits. It features a diagram with a power supply, 3 parallel branches, and switches S1, S2, and S3. There's also a picture of some hair straighteners.
11.1 just asks you to identify a circuit symbol for the diagram, a triangle pointing to a line inside a circle with 2 arrows pointing away.
That's an LED, right? Light emitting diode.
Exactly. 11.2 asks why the hair straighteners won't turn on if only switch S2 is closed.
Looking at the diagram, switch S1 is positioned right next to the main power supply before any of the branches.
Right, so if S1 is open, there's a gap in the main circuit. The MARC scheme says S1 needs to be closed to complete the circuit, otherwise no current can reach S2 anyway.
11.3 gives us the maximum power input of the straighteners as 120 watts. The energy transferred is 3.6 kilojoules. Calculate the time taken.
First, turn 3.6 kilojoules into 3,600 joules. We use the equation time equals energy divided by power.
So 3,600 divided by 120.
Which gives you exactly 30 seconds.
And the very last question of the paper, 11.4. Switch S1 is closed, then switches S2 and S3 are also closed. Explain what happens to the power output of the power supply.
This tests your knowledge of parallel circuits. By closing S2 and S3, you are adding more branches in parallel.
Which actually lowers resistance, right?
Yes. Adding parallel branches decreases the total resistance of the circuit.
And if resistance decreases,
the total current drawn from the supply increases.
And bringing it back to power.
Power equals potential difference times current. Since the current has increased, the total power output increases.
So turning on more parallel components draws more power. Makes perfect sense. And that concludes the entire June 2022 Higher Tier Physics Paper 1 walkthrough. We've hit every slide.